Okay, we spend a lot of time looking at the normal distribution and using the normal distribution because a lot of real world data tends to follow a normal distribution. That is, it tends to be centered on some mean value and it tends to be bell-shaped so that values that are very far from that center tend to be unusual and values that are closer tend to be more common. And likewise, that symmetry tells us that values tend to be a little bit under as often as they are over. So um, a lot of things do follow normal distributions. You can think of a lot of measurement processes like changes in stock price or things like measuring the daily output of a factory um, or the yield on some cropland. So uh, or any of those scientific measures, length or mass of something, they tend to follow a normal distribution, but not everything does follow a normal distribution. And so we're going to talk about in this lesson a new distribution and then look at how you go about calculating the probabilities and coming up with the expected value and the variance of this other distribution. Okay, but first I want to take a look at some actual data and look at how it's normal and what that means. Okay, so I've got here, these are delivery times. We could say that this is like UPS, times to complete a delivery route. And these are, so notice these are not actually, they're not discrete data because time is a continuous variable. And we see that we have fractional values here, and these are hours. So we've got the observation number and then the time it took to complete that daily route. So this is 7 hours and 62 hundredths of an hour. So this isn't actually base 60. This is not minutes. So this is actually 62 hundredths of an hour. And so if we just kind of browse through this data, what we observe, okay, we see that we've got, over time, let's say we've collected this data and we've got 51 observations. And we see that, they seem to be generally around 6, 7, 8, 9. So probably kind of a fairly fair work day. So I put a little bit of just a couple of descriptive measures down here at the bottom. So I've calculated the mean and I see that it's 7.46 and the median is 7.5. So one thing I can see right away is, well, it seems to be symmetrical. The mean and the median are about the same. But let's take a look at, getting a little bit more detail on the shape of this data. One thing we can do is under data and data analysis, we so right here under Fourier analysis and above moving average, which we'll be using later, we see we've got a histogram, and a histogram just lets you do frequency counts of observations that fall within certain ranges, and I'll show you what I mean. Okay, so the histogram worksheet here lets you select a range of values. So I'm just going to select these. Okay, our 51 observations. And it also lets me select bins. Often this is helpful because this lets Excel know how you want to chop up the data. So I'm interested in half-hour intervals ranging everywhere from 4 to 10 hours. So I'll just select these as my bins. So what it will do is it will take all of these observations and then put them into one of these bins. And then it will show me how many observations fell into all of these bins. And I'm going to go ahead and make sure that I have chart output selected here. So if I come here, okay, so there's my histogram. So again, histogram just shows us the counts of observations that fall into that. And we can see that we have a lot of observations here in the middle. And although it doesn't follow that very nice, like the theoretical normal distribution, it is pretty close. It does appear to be bell-shaped. It's reasonably symmetrical, not perfectly symmetrical. And the frequency of observations fall out quite a bit when you get far out from the center here. Okay, so we can see visually using the histogram that that this data, this delivery time data is, we can say that this is pretty much normally distributed. Okay, and using the we can see by comparing the mean and the median that it's also, not skewed too badly. Let's take a look at another visualization that will help us understand the shape of this data kind of thoroughly. If you select the data this way and then go to your insert ribbon, this thing over here lets you do insert statistic charts. So we can come here, and then down here is something called the box and whisker. We'll select that. Okay, so this provides a very convenient way to summarize the data and let us determine whether it's actually normal. So the way this works is it gives you these so-called whiskers here at the end, which show you the range of the data. So we can see that this line indicates that the lowest, the shortest delivery time was somewhere between 4 and 5, and the highest was somewhere between 9 and 10. And this gives us, this line right here shows us our median. So we see that the median is, between 7 and 8, as we saw down here on the worksheet. And this X shows us where our mean fell. And this box shows us the second quartile to the third quartile. So this interquartile range here. So we can see that this bar and this bar are not completely the same length. So it's not perfectly symmetrical. We do see that the mean and median fall right, pretty much right on top of each other here on this line as far as our visible resolution goes. Well, let's take a look at what happens if I kind of purposely throw in an outlier here. So it doesn't look like we had any outliers. Everything kind of fell within a decent range. But if I were to purposely say, okay, well, let's say we had a really slow delivery driver who took 13 hours. Okay. Let me go ahead and add that observation to this chart then and just regenerate it. So, okay. So I'll select all of these, and then again go to Insert and Chart. Okay, so now I see the way these charts work is they put an outlier outside this line here. So there's our outlier. Okay, and we can look down here and see that this outlier has pulled our mean up above the median. Just slightly. It used to be slightly below it. Let's change this outlier to, let's say we had somebody super fast and they were 3. So now we have an outlier on the bottom, and we see once again that the mean doesn't fall directly on the median. Okay, so now we can see that we have a bit of a left skew here. But for the most part, this is a very nice, this chart shows us that this data is very nicely normally distributed, which you would expect, considering the measurement process is, everybody completing the same task, and you have this center value, and it's unusual to have anything that's really completely outside the norm. Okay, but let's take a look at another data generating process that might not look quite so nice like this. Let's say I've got a roller coaster. Let's say I operate a roller coaster, and I want to start collecting a random variable, observations of a random variable, which is the times between runs. Okay, so that's all I'm doing. I'm going to start collecting data on how long it takes to, have all of the passengers get off and get, load new ones on and check the safety restraints and all that and give the thumbs up and run it. So I want to start collecting the data on the times between runs. And let's say that I observe that on average I have a rate, and remember that we traditionally denote a rate with a lambda, Greek letter lambda. I have a rate of, let's say, 30 runs per hour. Okay, so I have 30 runs per hour, and I start collecting data on the times between runs. Okay, so let's take a look at what this would look like. Okay, so I've got the data right here. Okay, so I can see that I've got 1 through 30. I've got 30 observations, and I see that I have 2 minutes here, 3 minutes here. It's gone as high as 6 minutes here, and it was actually gone 8, 9, and 12 over here. For the most part, it seems to hover between 2 and 3 minutes. So let's do the same thing that we did before and try to visualize what this data might look like. And I've provided bins here again. I'm interested in half-a-minute intervals from 2.5 to 10. So let's go ahead and insert that histogram. So I'll go to Data, Data ribbon, Data Analysis, and Histogram. Okay, this time I'll select this range. Shift-Control down will be a nice shortcut for that. Okay, and now I can select these as my bins, and I'll do chart output again. Okay, let's take a look at what these times look like. Okay, so now we have something that does not look anything remotely like a normal distribution. Many of the times are here down like below 3 minutes, and then as they get higher and higher, it seems like the sky is the limit. You could have mechanical problems, and this could just go on. So this right tail could go on quite a bit here, but we see that most of the times are up here, very on the low end of this. So we have this shape where it's very high up here near towards 0, and it slopes down like this and then keeps going. Okay, so remember that these are bins. So this is not actually a discrete probability distribution. This is a continuous distribution because it's time. So we can imagine that this is actually a smooth curve. Okay, so it turns out that there is a probability distribution that, much like the normal distribution, that allows us to handle data like this. And this data tends to emerge in situations where you are looking at the time between certain events. Okay, so much like when we were looking for verbal evidence of what kind of probability distribution before, when we said, okay, well, if we're looking for a count of something happening per unit of time, that's a discrete, and that's going to be a Poisson. If we're looking for a number of successes over a given number of trials, that's going to be a binomial. With an exponential distribution, and that's what this is, by the way, exponential distribution, and I'll explain why exponential in a second. But with an exponential distribution, this tends to model time between events. So time between. And so these can be things like time between customer arrivals, time between shipments, time between breakdowns, time between roller coaster rides. Okay, so this comes with a probability density function. Okay, so remember that with a continuous probability distribution, we don't have a probability mass function that will just give us a probability of observing a certain value. So we have this. Remember that with the normal, we had this. Our data looked like this, and then in order to find we can't actually look for this particular value, but we can look for the probability between some values, and then we just take this area. Okay, so the probability density function, the PDF, gives us this function that we can take the area under between two values, and that would give us a probability. Okay, so remember that this won't give you a probability because it is a probability density function. Okay, so let me explain what these variables in here refer to, and then show you how you can actually get something that will give you a probability. Okay, so as I said, this won't, because it's a probability density function. It only gives you the height of this function. Okay, so in this, lambda, so this is lambda is going to represent our rate, and e is the base of the natural logarithm. We looked at that before. That's around, let me make this a little neater. That's around 2.718 and so forth. So we've got that lambda there again, and then we've got that x, which is the value that we're asking about. So we could ask a question like this. Okay, so what is the probability? So again, we have to do a range here. So with the exponential distribution, we start over here on the positive end, and then this would go to positive infinity, and it looks like this. So let's take a look. If we look back here, this is very like our data here, right? Okay, so this is going to give us some kind of function that we can integrate to find a probability, and it looks like the right shape. So this follows an exponential distribution. Okay, so we can't really find, we can't just plug values in here and get a probability, but we want to be able to find the probability that x is going to be less than 3. So, taking our original example, so if the roller coaster runs at a certain rate, let's say 30 per hour, what is the probability that the time between runs is going to be less than 3? And so that's what this is going to enable us to do. But remember, much like this, we have to integrate between values. And so we have to integrate from 0 up to this x. So we need to find our area under this. So this is that function. We need to find the area under there to get our probability. Okay, our CDF. Okay. So I'm going to do just a little bit of calculus here, not a whole lot of terribly complicated stuff, but I want to show how we turn this into a CDF, a cumulative distribution function that we can actually plug values in and find probabilities. Okay, and we're going to do a couple of example problems, so this will be a little bit more concrete in a minute. Okay, so what we have to do then is, to get an area under a curve, is we have to integrate this function. So we're going to have to, and let's just make this more general here. So let's say, to get the probability that x is going to be less than some little x, this is going to be the integral from 0 up to x of this function. Okay. With respect to x. Okay. So the first thing we can do is just, lambda is just a constant, so that's just our rate, so we'll pull that out. Doesn't depend on x. Okay, now we'll just do a little bit of simple u substitution. So we'll set u equal to minus lambda x. So du is going to be equal to minus lambda dx. So 1 over, or negative 1 over lambda du is going to be the same as dx. Okay, so now we can substitute u and du in here with the appropriate adjustment. So we're going to have lambda integral 0 up to x e to the u du, but we have this minus 1 over lambda, so we need to include that, multiply minus 1 over lambda. And this is just a constant again, so once again, I'm going to pull it out here outside the integral. So we're going to have lambda times 1 over negative lambda, and then 0 up to x, and then e to the u du, okay, which is just e to the u. So I'm going to go ahead and in a single step combine these, so that's just going to be negative 1, and so this integrates, the antiderivative of e to the u is just e to the u, so we'll do e, and then we'll go ahead and back substitute that minus lambda x right here, minus lambda x, and we evaluate that from 0 up to x. Okay, so let's go ahead and kind of ran out of room here, so I'm going to come up here. So this will be negative 1. Okay, so this means to evaluate x at x and then subtract evaluating x at 0. So this will be e to the minus lambda x minus e to the minus lambda times 0. Okay, so and remember this will just be 0. E to the 0 is 1, so this will be negative 1 times e to the minus lambda x minus 1, and then we can multiply that negative through and just rewrite the order a little bit. And so this is going to be equal to, so positive 1 minus e to the minus lambda x. Okay, now this gives us something very, very useful. Okay, so this gives us the integral from 0 up to whatever x we put in. It gives us that area. Okay, so if we have a given x, we can and a given rate, we can just pop it into this, and it would give us that area that we need. We don't even need to look it up. Remember that doing this integral with the normal PDF was just very, very hard, but this was a fairly easy thing to integrate, and it winds up yielding a fairly nice function that we can use. Okay, so let's go ahead and apply this then, see it in action. Okay, so the cumulative distribution function for the exponential distribution, remember, we'll know to use this because we're looking for a time between So the probability of an arrival time, or time between, being less than some given x is just 1 minus e to the negative rate times that x. Okay, so this is just going to be just plugging stuff in, with the only trick being that you have to be careful to keep your units consistent. Okay, so let's do an example here. If I run the roller coaster 10 times per hour, what is the probability that the time between any two rides will be less than 3 minutes, or 0.05 of an hour? Okay, so go ahead and plug those values in there and see if you can come up with a probability. Okay, so we can just plug in here. So we have a lambda this rate 10 times per hour. So that's 10, and I'm just going to write per hour so that we can be sure we keep our units straight. And so we're asking about the probability that the time between any two rides is less than 3 minutes. Okay, so we've got this format here. So the probability, and I'm going to just use this notation. So the probability that it's going to be less than 3, okay? But remember that that's 3 minutes, and we actually expressed our rate in terms of hours. So let's go ahead and use the hours, which would be 0.05 of an hour, okay? Because 3 minutes is 5% of an hour. 6 minutes would be 10% of an hour, so 3 minutes is 5% of an hour. Okay. All right. So so then the probability. Let's go ahead and make this that 0.05. So the probability 0.05 is going to be equal to 1 minus e to the negative 10 times x, which is 0.05. Okay. All right, let's go ahead and throw that into Excel and see what we come up with. Okay, so it's just going to be equal to 1 minus, and then the way you express that e in Excel is just exp. Okay, so that says the exponentiation function is going to be taking e up to whatever you put in the parentheses afterwards. So that's going to be negative 10 times 0.05, negative 10 times 0.05. Okay, and so remember that this is our probability. This is the probability that the time between any two roller coaster rides, the probability that that time is going to be less than 3 minutes is going to be 0.39347. Okay, so, or like a 40% probability. So it has a reasonably good chance of being less than 3 minutes if it runs 10 times per hour. Okay. Now let's go ahead and, as always, I show you the formulas and the derivation, but of course Excel always has a shortcut because in the real world you can just use these shortcuts, and I introduce the equations and the probability, the derivations, just so that you kind of get an understanding of how they work. But of course we can calculate the same thing using a function in Excel, which is expon. Notice not exp, it's expon.dist. And then it just lets you plug in your x, your lambda, and cumulative, which in our case is always true. So in this case, our x was 0.05, and our lambda was 10. And we always put true here when we're trying to get probabilities from a continuous random variable. Okay, so we just enter the function this way, and we get exactly the same answer. Okay, so all this function is doing that same equation, 1 minus e to the minus 10 times 0.05. Okay. All right, so if I were to, let's just think a second here. If I were to ask, if I run the roller coaster, let's say 10 times per hour. If I run 10 times per hour, then so if I were to ask you what would be the average time? So what would be the average time between? Now notice that the output of the CDF here is going to give you the probability of a time. What's going to be the average time between those rides? Okay, so if I run 10 per hour, so that would mean, okay, well there's 60 minutes in an hour, right? So that would mean that if I run 10 per hour, then 60 divided by 10 is 6, right? So that would mean the average time between would be 6 minutes, right? So let's think more generally how we got to that. So if we said, okay, so 10 per hour, let's say our rate is 10 per hour, then that would mean that in, how often do they go? Well, that would be 1/10 of an hour. So if there's 10 per hour, each roller coaster leaves every 1/10 of an hour. So if they each go in 1/10 of an hour, then they could get 10 of them in 1 hour. Okay, so all we did was we did the reciprocal there, so 1/10. And so in general, the average for an exponentially distributed random variable, the average, that is, so the average time between, in this case, is going to be 1/the rate. Okay, so if I were to say, okay, well, if I do 20 rides per hour, that would mean I do the time between rides is 1/20th of an hour. Okay, so it's just the average is going to be 1/the rate. Okay, and so that's here on this slide. Okay, so the mean of an exponential distribution is given by just 1/the rate. Hopefully that last example made that clear. And it turns out that the standard deviation of this is also 1/lambda. Okay. All right. Well, let's go ahead and take a look at an actual problem from the homework and see if we can figure this out. So, given an exponential distribution with lambda equals 6, okay, lambda equals 6, what's the probability that the arrival time is less than 0.2? Okay, so let's do a sketch again, and remember that what we're doing, we've got this exponential PDF that looks like this, and we've got some x, and we're going to we need to find this area from 0 up to x, which we do by integrating, or because I showed what the integral was for that, we're just going to be applying the 1 minus e to the minus lambda x, and that would give us this area here. Okay, so what's the probability that the arrival time is going to be less than 0.2? So in this case, this x is going to be 0.2, and we need to find this area here. Okay, so we can just use this formula. Let's use this formula at least one time, and then we'll just go and do the function in Excel. So this will just be 1 minus e to the minus 6 times 0.2. Okay, so we'll just do it like that in Excel. So equal to 1 minus exp, okay, the negative 6 times 0.2. Okay, so 0.6988. Okay, so the probability that, so this area here gives us that probability, and the probability that it's less than 0.2 is going to be 0.6988. Okay, And so that's a 70% probability. So that's a lot of the probability mass that's under there. Okay. Okay. So now the next question asks us, so what's the probability that the arrival time is going to be greater than 0.2? Okay. Well, now it's just asking us about this area. Okay. So what's that area going to be? Well, we know that this is a density, right? So it's just going to be 1 minus this. Okay, so it's just going to be 1 minus 6.6988. Okay, so it's going to be 0.3012. Okay. Okay, so now it's asking us, okay, so what's the probability that the arrival time will be between 0.2 and 0.4? Okay, so now we've got another value out here. So we're saying this is 0.2 and this is 0.4. And we've got this new area in here. So this area. Okay, so we need to find out what this area is. Okay, so when we did this in, for the normal distribution, all we did was we took, two left tail probabilities, right? So we took the probability that it was going to be, less than 0.4. So this whole area minus the probability that x is going to be less than 0.2. Okay, and we've already calculated this one. We know that it's 0.6988, and we don't have this one yet. But let's go ahead and just do this whole thing in Excel using the Expon function. Okay, so I'm going to do, so the probability that it's less than 0.2, so this is going to be Expon, okay, Expon dist. So the probability that's going to be less than 0.2, given a lambda rate of 6, and we use true here because it's continuous. Okay, and okay, so we've already got that one, but now we need to subtract out. Okay, so actually we're gonna subtract the 0.4. So 0.4. Okay, and then we have to subtract out the expon dist of 0.2 with the lambda rate of 6 and true. Let me see if I can zoom in a bit here. We're fairly small here. Let's go into, oh, it's a little bit better. Okay, so no, it doesn't help. So we're using this function to calculate the probability that it's less than 0.4, and then subtracting the probability that it's less than 0.2. So this is going to give us this area in here, and that wound up being 0.2105. Okay, so 0.2105. Okay, so now they're being a little bit sneaky here. So now they're basically doing the opposite of this area, right? So we just did this area in here, and now it's saying, okay, what's all this area? Well, if you think about it, it's going to be 1 minus whatever this area was. Okay, so this area was 0.2105, so we can just do 1 minus 0.2105. So that was 0.7895. Okay, and you could do that. You could do that in a different way, you could find this probability, right? So you could do this left part. So it's going to be this plus this. So you could do the probability that x is less than 0.2 and then add it to, and then how do we find this? Well, that's a right tail probability. So that's going to be 1 minus probability that x is less than 0.4. Okay. Okay, and if you do the algebra, you see that they wind up being the same. Okay. All right. Well, that'll conclude the continuous distributions. So we've now covered descriptive statistics, discrete probability distributions, and continuous probability distributions. There's a lot of material to cover in a short amount of time. Again, I hope this helps, and please let me know if you have any questions.